Subject: Signals and Systems. Topic is Discrete-Time Signal. Lecture delivered by Indranil Sarkar. Discrete-Time Signals. First, we have to know what is sampling. Sampling is the acquisition of the values of a continuous time signal at discrete points in time. Next, xt is a continuous time signal and xn is a discrete time signal. That means continuous time signal is represented as a discrete time signal using sampling, where xn is equal to x n t s and capital Ts is the time between samples. Discrete time exponential and sinusoidal signals. Discrete time signals can be defined in a manner analogous to the continuous time counterpart. Xn is equal to a sine 2 pi small n by capital N0 plus theta, or a sine 2 pi f0 n plus theta. This is a discrete time sinusoidal signal. In exponentially, it is represented as xn is equal to a to the power n. This is the discrete time exponential signal. Here small n is equal to discrete time, a is equal to amplitude, theta is the phase shifting radians, n0 is the discrete period of the wave. 1 by n0 is equal to f0 is equal to omega 0 by 2 pi is equal to discrete frequency. Here the discrete time sinusoidal signals. Examples of the sinusoidal signals in discrete time. Here the periods are changed and the samplings are changed. According to change of samples, the figure looks like this. Discrete time unit step function or unit sequence function. Here un is equal to 1 when n greater than equal to 0 and 0 when n less than 0, and this is called the unit step function. Here we see that in the right side we will get the value, and the value is 1 and it is uniform. That is why it is written as n greater than equal to 0, the value is 1 always, and in the negative part or in the left part it is 0 when n less than 0. Discrete time unit ramp function. Ramp n is equal to n when n greater than equal to 0 and 0 when n less than 0, and it is represented as summation of m is equal to minus infinity to n u m minus 1. Here the ramp signal is represented in a discrete form. Discrete time unit impulse function or unit pulse sequence. Here del n is the unit pulse function, and the del n is equal to 1 when n is equal to 0, and del n is equal to 0 when n not equal to 0. That means only n equal to 0 there is a value of del n. So we can represent del n is equal to del an for any non-zero finite integer a. Unit pulse sequence. The discrete time unit impulse is a function in the ordinary sense in contrast with the continuous time unit impulse. It has a sampling property. It has no scaling property. That is, del n is equal to del an for any non-zero finite integer a. Operations of a signals. Sometimes a given mathematical function may completely describe a signal. Different operations are required for different purposes of arbitrary signals. The operations on signals can be time shifting, time scaling, time inversion or time folding. When this is the main signal xt, when the signal is t plus t0, that means minus 2 minus t0 and 2 minus 0. So the signal becomes minus t0 minus 2 and minus t0 plus 2. The signal shifted to the left, and signal is the advanced signal and represented as xt plus t0 over here. It is represented over here when a greater than 1, the graph of the function shrinks. Here the value of a is equal to 2, so the graph shrinks. The period of xt is 2 and the period of yt is 1. Time scaling. Here is also yt. Now first find wt is equal to y3t and vt is equal to yt by 3. Now the signal yt is equal to, represented over here in the top, yt is started from 0 to 3 and the height is 2. Width is 0 to 3 and the height is 2. Now the signal wt is equal to y3t. That means the signal speed up. When the signal speed up with the value a is equal to 3, the signal becomes, and the graph shows that it will shrink. At wt is equal to y3t, which is speed up by 3, represented in the middle figure, where we see the signal started from 0 and end at 1 and the height is same, that is 2. That means here t becomes 3t. That means 0 to 3 becomes, over here is 0 to 1. That means the signal shrinks. Now in the vt is equal to yt by 3. Now t is represented over here as a t by 3. That means signal should be expanded. Here we see that the signal is 0 to 3. When we are using t by 3, the signal is expanded 3 times. That means 3, 6, 9. If we consider 0 to 3, there is a 1, 2, 3, and for that the signal is here 3 times. That is why it is represented over here as a 3, 6, 9, and the height is again 2. So in case of a less than 1, the signal expanded, which is represented in the below figure. Time reversal. Time reversal is also called time folding. In time reversal, signal is reversed with respect to time. That is, yt is equal to x minus t is obtained for the given function. That means if the signal is xt, for the time reversal the signal becomes x minus t. Here the signal xt, which is represented from t1 to t2. Now when it becomes yt is equal to x minus t, it is the just replica or just reversed, or you can say this is the mirror image. The signal goes to the opposite direction and it started from minus t2 to t1, minus t1. Okay, that is the time reversal technique. Now this is the time shifting. Here n greater than, n tends to n plus n0. n0 is an integer. Here the signal represented over here is gn. The signal starts from minus 1 to continues to 9, where the values are represented in the right side. For n is equal to minus 1, the value is 1. For 0, 2. For 1, 3. 2. For n is equal to 2, the value is 4, and so on. And when n is equal to 10, the value becomes 0. This is the signal of gn. Now when gn plus 3, now this is the time shifting, means we are shifting it. How much time we are shifting? N is equal to minus 3. That means the signal is shifted in the left side, and signal started from minus 4, because in the previous case of gn the signal started from minus 1, and for gn plus 3 the signal shifted 3 places in the left side. So signal started from minus 4, and again the signal represented in the same manner. For the minus 4 it becomes minus 1, for the minus 3 it becomes 0, minus 2 for 1, minus 1 for 2, and 0 for 3, and in this way it goes. So we will get for n plus 3 and for gn plus 3. Operation of discrete functions. Scaling. Signal compression when n tends to kn, k an integer when greater than 1. Here we see that gn. Here the different type of signals are represented. Same signal, it started from 0 to 4. We see that from 1, minus 1 to 10, the signal is represented as like the previous, but we are taking the values of A, B, C, D, E, and so we are denoting those in the right side. N is equal to 0, 1, 2, 3, 4, and in case of G2n, the signal becomes, for N is equal to, we take 2n. That means we are taking the even functions. That means we are ignoring 1, 3, these portions. That means the signals are doubled. Means for N 0, 1, 2, 3, 4, but in case of 2n it becomes 0, 2, 4, 6, 8. For G2n the signal becomes 2, 4, 6, 8, 10. In this way. That means signal is compressed and represented in this way. Thank you.